Okay, so let's quickly refresh what we did last time. So we talked about the Fermi gas, which is the gas of free electrons in a metal. And if you remember, we derived a few relations. So let me remind you of those. So this is your Qx, Qy, and Qz. And then by employing periodic boundary conditions, you got the values of these Qi's, and the Qi's what they turned out to be quantized. So Qi, the ith component being 2 pi by L times Ni, where Ni belongs to a set of integers and L is the length of your sample, right? So sample is in the form of a cube of size L cross L cross L. Okay. So with this, when you started building up the ground state, so the ground state is the state at t equal to 0. Ground state refers to the state at t equal to 0, and this is the state where you fill in electrons obeying Pauli's exclusion principle, 2 electrons per state, not per state, per q point. So each of these are q points. The q point has a coordinate. So if you take any arbitrary q point has a coordinates qx, qy, and qz, and these are the quantum numbers of the problem along with the spin of the electron, right? So there are 4 quantum numbers, qx, qy, qz, and then you can have a spin 1/2 or -half. So your total number of, let's say the total number of electrons in the system is n. The volume of your sample is V, okay, which is equal to L cube. Then the number density n is nothing but n over V. Okay. And then when you start filling in these electrons in these states, then at t equal to 0, you get a very sharp boundary region inside of which all the quantum states are fully occupied and outside they are empty. So this is known as the Fermi sphere or Fermi surface, which happens to be a sphere in the case of free electrons. And the Fermi surface has a certain radius, which is q sub f, and we obtained a formula for it. You remember that? That formula is 3 pi square n to the power 1 by 3. That it depends only on the number density of your electrons. So if the number density is large, this is going to be a larger Fermi surface, and so on. Now once you know Qf, you can immediately get the Fermi energy from Qf, and that's h bar square Qf square by 2m, where m is the mass of electron. Once you know the Fermi energy, you can estimate what is known as the Fermi temperature, Tf, which is nothing but Ef divided by Kb. Okay, so you can just plug in, and then you can also get Vf, which is the Fermi velocity, which is the velocity of electrons that are located at the Fermi energy. Okay, so this will be simply, Vf will be simply related to h bar Qf divided by the mass of electron. Now for a typical metal, sodium or copper or aluminum, let's list the values of these quantities. So once you know n, you can get all these quantities, isn't it? It's a simple exercise. And n you can know from the number of electrons that the atoms in that particular element donate to the conduction C. In the case of sodium, for instance, 1 electron, and from the lattice parameter of the sodium you can get this number n will come out to be 2.5 into 10 to the power 22 electrons per centimeter cube. That is the density of electrons in sodium metal. Okay. So, if I were to write these numbers for sodium metal, then the Fermi energy is the first thing, QF will be the first thing that I would estimate, and this QF is of the order of 10 to the power 8 centimeter inverse. Once you use it over here and you work your way through the unit conversion carefully, you will see that this energy is of the order of 4 electron volts. Now, how much is 4 electron volts in terms of temperatures? In terms of temperatures, this is a pretty high temperature. This is about 37,000 Kelvin, right. So, in general these temperatures are of the order of 10 to the power 4 Kelvin. The Fermi temperatures are of the order of 4 Kelvin. What this means is that unless you heat the electron gas to such high temperatures, you won't see the classical nature, right. So, they are highly degenerate at 0 temperature. They remain degenerate quantum gases even at room temperature. Unless you increase the temperature to such high values, this is insanely high, of course. It is absurd to think that you can increase the temperatures to such high values. But the point is that then what it means is that for all practical purposes, the electron gas is a quantum gas, right. And the velocities are of the order of 10 to the power 8 centimeters per second. And let me just remind you that this is about a factor of 10 bigger than the velocity that you would estimate using the classical laws, half mv square equals 3 half kT, by using that. So, that we called V naught, if you remember, that is the thermal velocity. So, if you compare it to the thermal velocity or thermal velocity, then the thermal velocity is given by this formula, half mv naught square is equal to 3 half kT. So, even at room temperature V naught is of the order of 10 to the power 7 centimeters per second, which is lesser than the Fermi velocity at 0 temperature. So, this is the velocity at 0 temperature, remember, because all these are the properties of the ground state. Okay. So, now what next? We also derived the formula for the density of states. So, let me just write it down here. You remember we worked out the density of states. So, the definition of dE, density of states, this is called density of levels or density of quantum states per unit volume of the sample. Okay. And a quantum state is what? A quantum state is just this Qx, Qy, Qz and the spin quantum number. These 4 quantum numbers, they define a quantum state, right. And this S can take 2 values, plus half or minus half, repeating myself. So, this is what. And we derived a formula for dE. Remember, the definition is number of states in the energy range between E and E plus dE per unit volume. So, using that we derived the formula, which turned out to be 1 over 2 pi square times 2m by h bar square to the power 3 halves square root of E. The point to remember, all these are constants, right. So, this is density of states in 3D for an electron gas is proportional to square root of E. Okay. Now, this will be a homework problem, some manipulations. Suppose you have to find density of states at EF, density of states at EF, at this, what is the density of, so you just need to plug in EF for E, and then you can if you have to reduce it further, you can put EF in terms of this and then this in terms of this, so you can find the EF. So the homework problem is that you have to prove that this is 3n divided by 2EF. Okay. And you can also write it in terms of the QF vector, yeah, and then it will be simply m times QF divided by pi square h bar square. Okay. So this is a straightforward, using all the relations that I have listed here, using this you can derive this relation. Okay, and this is a homework problem for you to do this. Now we go further and we want to now work out the energy per electron in the ground state, energy of the electron gas per electron in the ground state. Okay. So, I am erasing this part, hoping that you would remember some of the things for the future part of this lecture, and later on also in the future lectures also these things will surface time and again. So, what we are going to do is find out energy, or I should say ground state energy, energy at t equal to 0, that is the ground state energy, per electron in the ground state. In another words, what we have to do is to find the total energy of the electron gas at 0 temperature and divide it by the number of electrons. That is all you have to do. So, what you have to do is you have to take all the electrons at 0 temperature and go on adding up their energies. That is it. It is as simple as this. Okay. So, how will you do it? So, let us fix a symbol for it. So, let us first say that U naught is the ground state energy of the electron gas, total ground state energy, and then we will divide it by, when we will divide it by n, we will get what we want, and this I am going to designate by u little n n for instance. And sometimes it is useful, or in exams you are asked to find the energy of the electron gas per unit volume, in which case it will be u naught by V, and we are going to use this notation u naught V. Okay. So, the main thing is to find u naught. Okay. How will you find that? Yes, you have to do a lot of integrations in order to get this. So, not a lot actually. So, once again we will do the same thing. We will think of a shell at a distance e and whose thickness is dE, right. We will get the number of q points inside, number of quantum states inside, and then the energy of each of these states is approximately E, because they are at E distance, they are between E and E plus dE. So, we will get the energy of all the electrons that reside within that shell, and then we integrate from 0 to QF, and we will get the total energy, right. then that will be the calculation for u naught. The other method is that you already have an expression for dE, right. So, all you need to do is dE is the density of states, right. So, density of states at energy E, right. So, if you multiply it with E, you will get the energy of all the states that are at E, right, and then you integrate it from 0 to EF and you will get your answer, right. Either way you can get it. Okay. So, let us take the first path. So, which will be simply this, that you know at a distance q, you considered a shell whose radius is q and whose thickness is q plus dq. Okay, so it's a so the volume of this shell, the elementary shell, will be 4. Yes, please. 4. What will be the volume of the shell? 4 pi q square dq. That's the volume of the shell. If I multiply this volume by the density of q points, right, then I will get the number of q points within the shell. And what is the density of q points? That's 8 pi cube by v, isn't it so? Oh, sorry, v by 8 pi cube. 8 pi cube by v is the space that each q point takes, right. So, that is simply v by 8 pi cube, and I should multiply it with 2 to get the density. Now, this is the density of quantum states actually. So, this is the density of quantum states, and I multiplied it with the volume of the shell. So, that gave me this quantity gave me what? The number of quantum states or the number of electrons in the shell that I have considered. Now, each of these electrons has an energy E, right. So, I multiply it with E, right, and then I integrate this from variable of integration is q. So, from q equal to 0 to q equal to qf. Why? Because I know that beyond qf the states are unoccupied, there are no electrons, right, and I can write E as E can be written again in terms of q as h bar square q square by 2m, right, that you can do. You can plug that in here, and then you will get q to the power 4. You will integrate it, you will get q to the power 5 by 5, right, and if you do everything carefully, which you would, then you should get something like this: v h bar square over 2 pi square m and then you will get q f power 5 raised to the power 5 divided by 5. So, that is the expression for u naught. Okay. Now, we recast it in terms of little n, because that is the quantity we know, or in terms of Fermi energy. So, we can do that. For that, we have to use the relation between qf and n, right. You remember that relation? That is the only relation that we need to remember. Everything else can be then derived. It is just 3 pi square n raised to the power 1 by 3, right. So, if you plug in that over here and carry out some simplifications, okay, then you should get this quantity u naught to be. So, everything is okay till this point. Okay, so, I will leave the intermediate steps, plug this in here, do the simplification, and you will get lot of factors cancelled out. So, what will remain at the end of the day is that u naught is equal to 3 h bar square QF square and five which you are carrying from here and 2m which you are carrying from here, everything else will get cancelled out very beautifully, and of course the volume will remain. So, the catch here is that you will write this in terms of little n, and then you will write little n as capital N by capital V, right. So, that is the catch, and so here you will also get a capital N. So, this is what you are going to get if you will do everything nicely. So, this little n should be expanded further in terms of N by V, and then you will be remain with this. Now, you can see that this quantity is nothing but EF, isn't it so? This is EF, and this n you can bring down. So, you can divide on both sides by n. So, what you will get is the quantity that you want, little u n, which is nothing but 3/5 of EF, 3 by 5 of EF. So I mean, I didn't do anything great here. I mean, just calculated the ground state energy using a very simple logic, which I believe every one of you followed, and I got this relation. This relation is interesting and important, and I hope you will remember it. So, often this is asked in the exams, find out the ground state energy of an electron gas per electron, per particle. This is what it is. If you have to find the same thing as this, that also you can do, right. Then you will divide on both sides by V, and so you will have a little n sitting here, right. Okay, good. Now, we go further, but before that just want to highlight that this quantity for a classical gas would be how much? Sorry? 3 by 2 kBt, and T is 0, and T is 0, it will be 0. So, for a classical gas, the ground state energy would be 0, right. Each particle has 0 energy, because it is a classical gas. Energy at any temperature T is 3/2 kBt, right. On the other hand, the ground state energy of a Fermi gas is a very, very high number, because you know that this is of the order of 10 to the power 4 Kelvin, right. This is a very large number. Okay, so, the next thing that we are going to look at is this, that we took this our sample to be a box. Okay. Now, if we compress this box from all sides, which means isostatic compression. So, if we do that by applying pressure, external pressure, so what is going to happen? Let us try to analyze this situation. So, you are increasing the pressure, you are putting an external pressure, and this you are trying to increase the pressure in order to compress the electron gas, right. So, what it will do is, it will what will it do to the volume? If you will apply pressure, what will happen to the volume? The volume will squeeze, the volume will decrease, right. So, the volume will come down. If the volume will come down, then what will happen to this little n? Remember, this little n is the number density. The number has not changed, the number of electrons are not changing. What is changing is the volume, you are compressing it. So, since you are decreasing the volume, n would increase. So, n would go up. Since n would go up, what will happen to QF, the Fermi wave vector? That would go up, right. QF would go up. So, this implies that QF would go up. If QF would go up, what will happen to EF? That's the Fermi energy. That would also go up because the Fermi energy scales with square of QF, right? So this implies that the Fermi energy would also go up. And if the Fermi energy will go up, what should happen to U, which is just proportional to the Fermi energy? So this will also go up. And what does that mean? That means that the ground state energy of the electron gas would go up. Now, any system, whether classical or quantum, likes to keep its energy at minimum, right? So the electron gas would not like this whole scenario, right? So it will resist this compression. And the resistance to the compression is quantified in terms of bulk modulus, right? So we are going to now calculate the bulk modulus for the electron gas, right? So the message that comes out from here is that the electron gas would resist a compression. And what is preventing? Is it the classical electron repulsion which is preventing us from compressing the electron gas? You remember, we have not even considered the Coulomb repulsion between the electron. So this pressure is the degeneracy pressure. It's the same pressure that exists in the neutron stars. Okay, so that's a very interesting problem that you often get in the exam, the problem of neutron stars, because in neutron stars also you have the spin one-half particles, right, and you treat them at par with the electrons in a metal, and you find out the quantities that we just found out over here. Okay. So the electron gas in a metal, so or free electron gas, Sommerfeld model. So electron gas resists a tendency to compression. Resist compression actually, has the tendency to resist compression. Has the tendency to resist compression or resists compression. So before embarking on the calculation of bulk modulus, let's calculate the pressure of the electron gas. Just as the classical gas exerts a pressure on the walls of the container that holds it, the electron gas also exerts. So once again, very quick, small calculations. So the pressure at 0 temperature, that's given by pressure is the change in energy with respect to volume, keeping the number of electrons fixed. Okay, so del U del V with a negative sign, of course. Negative because it's resistance at a fixed n, right? U0 because we are working it out at 0 temperature. You know the expression for U0, it's a trivial exercise. Okay. So we know that U0 is nothing but 3/5 of the Fermi energy times n, isn't it so? Right? And we have to take the derivative with respect to the volume. Now the volume term is not here, but the volume term is here. This is volume dependent. How is it volume dependent? Because it depends on QF, QF depends on little n depends on V, right? So you just need to put in expand and then take the derivative once you have expressed it in terms of V. So I don't even know, I'm not sure if I should do it fully. So I'll take some shortcuts. So it will be 3/5 and then you plug in EF, EF will be h bar square QF square by 2m, then you put for QF 3 pi square n to the power 1 by 3, then for n you put n by V. So you will pull out a V dependence which will be V to the power 2 by 3 in the denominator. When you will take its derivative, you will get V to the power 5 by 3 in the denominator. So you keep that 1 v. So you can write v to the power 5 by 3 as v to the power 2 by 3 into v. So this v to the power 2 by 3 can again be merged back to get EF, and you will have remain with 1 v in the denominator, and you will remain with minus 3 by 5 prefactor, right? Minus 3 by 5, minus 2 by 3 prefactor, because you are differentiating 1 by v to the power 2 by 3, right? So what you are going to get is then you are going to get your EF back. You will get 1 by v, and you will get a factor of minus 2 by 3. Is that right? I mean, I did it very fast mentally, but it's not more difficult than that. So this guy will get cancelled out with this. Remember, there was a negative sign over here. This is after taking the derivative, by the way. This is the pressure. I have already taken the derivative. Huh? So this gets and there was a minus sign over here. So this minus will become plus. Okay, 3 and 3 will get cancelled, and this quantity is nothing but EF back. Okay, so what you have then is simply so you will have 2 from here, 5, and then of course EF, and then of course you are carrying a n with along with it, which I should write here, right? ये n भी तो था ना, इसको भी मत छोड़ो. So this n will be there, and then in the denominator you have the v. Okay, I'll make use of this formula, which I derived somewhere here. No, sorry. Yes, I can rewrite this. So EFN can be written as 5 u naught by 3. This line little readjustment. So you will get pressure in term EF naught n can be replaced by 5 u naught by 3. That you do 5 u naught by 3. So 5 and 5 will get cancelled out. So you get 2 u naught by 3v. So 2 u naught by 3v, and u naught by v is our little u at a fixed volume. Sorry, for per unit volume. So this is nothing but 2 by 3 u naught v. So that's the expression for the pressure. Now that we have the expression for the pressure, we can go ahead and work out the bulk modulus using this scheme. So how do you define a bulk modulus of a material? So if you apply a pressure P, delta P, then the volume goes as decreases. So it is minus delta V over V, right? And the constant of proportionality is the bulk modulus. So this quantity B over here is the bulk modulus. All right. So let's use this recipe to get B. So from this you can write an expression for B. The expression for B would then be simply minus V times del P del V at a fixed n. So this time we have to take the derivative of P to get the bulk modulus. Okay. So let's do that. It's like taking the second derivative of u naught. So you already know what is going to happen. So it's like, you already took the derivative of u with respect to v, right? So P is this. So therefore B would be minus V del by del V of P, and P is nothing but this quantity 2 u naught by 3, 2 by 3 u naught by v, or maybe 2 by 5 EF n by v. This is one step before this, it was in EF, in terms of EF, right. So, that is what you have to do. Now, once again you can plug in EF, because EF has the volume term. So, you write EF, then you write EF in terms of QF and QF in terms of little n, and little n as n by v, right. So, if you do all that, what will you get? You will get, like before, you will get v to the power 2 by 3 in the denominator, but 1 v is already present. So, you will have now v to the power 5 by 3 in the denominator, and when you will take the derivative, you will get 5 by 3 as a prefactor, minus 5 by 3 as a prefactor, and 1 by v to the power 7 by 3. Now, you can write 7 by 3 as 5 by 3 and 1, right. So, 5 by 3 you can bring again back here, right. So, what you will get then is this. What you will get at the end of the day is this 10 over 9 u naught by v, or you can say 10 by 9 u naught v. That will be the expression for the bulk modulus. Okay. You can also recast it in the form of EF, because you know the relation between u naught and EF. U naught is how much? 2/5 of EF or something like that. 3/5 of EF, you know that u naught is 3/5 of EF. So, you can always manipulate them. So, you can also write B. I mean, in exam you can be asked to prove that B is equal to this, or you may be asked to prove that B is equal to 2 by 3 NEF, or you may be asked a series of questions with part A saying that write EF in terms of this u naught, derive the first relation, then after that the pressure for the electron gas and the bulk modulus and so on. So, it looks very dry. The lecture looks very dry because this is like some kind of a maths going on the board that normally happens in lectures that are more theory oriented. I am not criticizing it. What I am saying is that that there is some fun in that, but I cannot possibly convey that because I am not probably doing things very elegantly. So, let us come to the crux of it. We have obtained the bulk modulus. How does this compare with the value of bulk modulus for the metals? That will give us an idea of what is the contribution of free electrons, because we know that in metals, besides the electrons, free electrons, there are also these ionic cores, right. And when you will apply pressure, when you will try to squeeze a metal, the ionic cores will also play a role, right. So, right now we have not considered them. We are just considering a metal as a free electron gas, right, as if it is a gas enclosed in a box, and the ionic core is playing a role which is to neutralize the charges. That is it. I mean, it is a uniform positive background, right. So, with all the simplifications that we made, let us see what is the value of, so for various metals, B which you get from the theory. Which theory? The free electron theory, because in our course we will go on revising this theory, going to make it better and better and better, and eventually match everything with the experiments, right. And this is B from the experiments, and the units are 10 to the power 8 dynes per centimeter square. You can also write it in SI units. So, for sodium metal, one of the classic metals, we always take example of sodium. For sodium, the free electron model predicts that the value of bulk modulus should be 9 into 10 to the power 8 dynes per centimeter square, and the value that one measures from theory is close to 6.4. And you would say, wow, I mean there is some overestimation, but not bad, Not bad, right? Order of magnitude is correct. You are getting 9 into 10 to the power 8. The experimentalist measured 6.4 into 10 to the power 8. Take one more example, cesium, right, the heavier alkali metal. For cesium, this value, calculated value is 1.5 and the measured value is 1.4. I mean, you don't need anything better. Third is copper, third example, where the discrepancy is quite significant, right. So, what you see that in some cases, especially in the case of heavier alkali metals, the bulk modulus predicted by our theory is fairly close to the experimental value, whereas in the case of transition metal elements like copper or other examples which I have not named here, the free electron theory grossly underestimates the value of the bulk modulus. However, the good thing is that in all cases, I went from to different parts of the periodic table, in all cases the order of magnitude prediction is correct, which means that the contribution of free electrons to the bulk moduli of metals is quite significant. It is not something that we can simply throw away. Okay? That is the basic message that we have. And of course, it is as is written in the book. So I will rather prefer to read it from the book, because this is like the Bible of condensed matter physics. And when something is written here, I don't need to change the language. So it says that the agreement for heavier alkali metals is fortuitously good, but even when is substantially off, for example, as in the case of copper, noble metals, it is still off about the right order of magnitude, though it varies from 3 times too large to 3 times too small through the periodic table, through the table which they have given. So, I have not listed all the metals there. So, it is not only large, it is not only small at places, it is also larger at places. For instance, here it is larger, here it is smaller. And then it says, it is absurd to expect that the free electron gas pressure alone should completely determine the resistance of a metal to compression. But table 2.2, where these values are listed, demonstrates that this pressure is at least as important as any other effects. Okay. And the other effects that he has not mentioned here are the effects of the lattice, which comes later in this book. Okay. So, we did the lattice first. Now, I will come to the most interesting part of this lecture and the most significant trump, the success of this model. You remember the specific heat of electron gas, classical gas, is a constant, because the energy is 3/2 kBT and the specific heat would then be 3/2 kB, and this should be temperature independent and this should be a constant, right. But I told you already while we were reading Drude's model that this value at room temperature is 100 times larger than the actual value, measured value that the experimentalist measured. And the other thing that the experimentalist measured was the temperature dependence of this specific heat, and they found that the specific heat actually varies with temperature linearly, okay, for a very wide temperature range. Okay. So, these two observations can be very easily explained using the model that we are working with. Okay. So, in order to do that, we have to look at a couple of things. So, at t equal to 0, you know, the situation is rather straightforward. At t equal to 0, you say that the quantum states, so I am going to write Qs for the quantum states. So, the quantum states that are below EF, whose energy or whose wave vector is for whom Q is less than QF, or for whom E is less than EF, they are all occupied, fully occupied, right? Their occupancy is 1. Let me put it this way. Their occupancy is 1. And when Q is greater than QF, all the states above QF, their occupancy is 0, or the occupancies are 0, right? Now, what happens at a non-zero temperature? Because that is where the question of specific heat also will come, right? You measure specific heat. Specific heat is the heat required to increase the temperature by a unit Kelvin, by 1 Kelvin, right, of a specific amount of solid, 1 mole, 1 centimeter cube or whatever. So, if T is non-zero, what is going to happen? So, what is your guess? What will happen? So, just look at this Q space, the wave vector space. So, last time also I gave you the hint. At 0 temperature, this surface is very sharp. This demarcation is very sharp, right? Below QF, all filled. Above QF, no filling, 0 filling, right? But when you start increasing the temperature, and let us say at some temperature T, what's going to happen is that the states that are within kBT of the Fermi energy, from that states, the electron will be excited to the states that are kBT, that are within kBT above EF of the Fermi energy. Okay? An electron which is residing deep, we say, which is buried deep inside the Fermi level or inside the Fermi surface, that electron cannot, the probability of exciting that electron is minuscule. The reason is that the thermal energy which is available to the electrons is of the order of kBT, because your temperature is T, and kBT is a very, very small number compared to EF. So, basically you are in this little region around EF, this itself is quite exaggerated. So, you are in this region. So, all the states in this region, their population will get reorganized when you will increase the temperature. But deep inside the Fermi energy, Fermi surface, everything will remain as it was before, because the electrons there, they do not have enough energy, they do not have states, unfilled states that they can occupy by exciting themselves, because the electron, the state which is here is filled, the state kBT above it is also filled, the state kBT above it is also filled. So, even if the electron has that thermal energy, where will it go? It has no free states to go, whereas an electron which is within this white belt, if it gets kBT energy, what will it do? It will start exploring the states that are located right outside the Fermi surface, because there are states and those states are empty. So, these electrons that are at the Fermi surface, these electrons will start exploring these states, whereas the electrons that are located deep inside the Fermi surface, these electrons are not seeing any free state around them, because all the states around them are filled as they were before at 0 temperature, is not it so, right? So, this is a very important concept, this is a very important point, that only the electrons that are near the Fermi energy, Fermi surface, how near? Within kBT of the Fermi energy, will be excited to the states outside the Fermi surface. The electrons that are buried deep inside, they will remain the way they were, right. So, you understand, in any transport or thermodynamic property, only a very small fraction of electrons participate, because these are the electrons that get excited, right. This is a very important point. So, now the question is that, you know, when you will start increasing the temperature of your electron gas, some electrons will start exploring the higher lying states, but some will remain within the Fermi surface, right, because this is a statistical process. I mean, even these electrons which are in this shaded area, even this number is humongous, isn't it? This is a very large number, because total number of electrons that you are dealing with is 10 to the power 23. The electrons that are residing at the Fermi energy is also a very large number, right. You can estimate that number because you know now the density of states at Fermi energy, right. So, it is also of the order of n, right. So, the point is that how would you know which state is empty and which is not, because it is a statistical process, right. So, that is known by this distribution function. The distribution function for electrons and for fermions in general is given by F equals, so F, let me write it as F E, F of E is equal to 1 over exponential E minus mu by kT plus 1. This governs the behavior of. So, what is, let me first describe these quantities. So, what is F? F is the probability of probability that the state at energy E is occupied. And 1 minus F would be the probability of the state being empty. And in this case, of course, at energy E there are very many states. So, you may as well write it as states. So, the probability that the states at energy E are occupied is given by this quantity. What is the quantity mu? Rest of the things you know. E is the energy of the state, quantum state. KBT you know. What is mu here? Yes, the quantity mu is called the chemical potential. Okay. So, if F is the free energy of your system, Helmholtz free energy, how do you write that? Helmholtz free energy is simply U minus Ts, where U is the internal energy which we just calculated at 0 temperature, but not at non-zero temperature, and T is the temperature at which we are talking about the energy, and S is the entropy. Okay. So, if F is the Helmholtz free energy, then mu is simply F n plus 1 minus F n. What does it mean? It means the energy required at any given temperature, the energy required to add an electron. In this case, we are talking about electron, but in general a particle, a fermion in a system, you know, the energy that is required to increase the number from n to n plus 1 is called the chemical potential, right. So, in this case, in our case, let us try to see the interpretation of mu. So, if you plot, if you see this quantity at 0 temperature, if you put T equal to 0, as T goes to 0, what will happen? How will this function behave as T goes to 0? Let us try to analyze it. So, at T equal to 0. So, at T equal to 0, what will be the value of this quantity, this factor? Correct. So, it depends on the relation between E and mu, right. So, if E is less than mu, then this quantity will become 0 as T at T equal to 0, right, because it will be e to the power minus infinity, which is, and in the other extreme it will be infinite, right. So, therefore, what will be the value of this function? So, at t equal to 0, your function f of E is equal to 1 if the energy of the quantum state is less than mu, and it is 0 if E is greater than mu. Right? But this is what we have in fact in the ground state that we are working with. When the energy is less than EF, the ground state is occupied, the quantum state is occupied, and when the energy is greater than EF, the quantum state is unoccupied, right. So, that means this function basically describes, if this function describes the probability of the quantum states being occupied or unoccupied, then at 0 temperature mu plays the same role as E of F, the Fermi energy, because if the energy is greater than Fermi energy, this function is becoming 0. If the energy is less than the Fermi energy, then this function is 1, right. So, what that means is that, so here you go. So, if you plot F against energy, then at 0 temperature, at t equal to 0, how will this look like? It's a step function, right. It's a step function which looks like this, right, and this point is mu, this is mu, and we just proved and we know that at 0 temperature this is the property of our system also. So, therefore, for an electron gas in a metal, this mu is equal to EF at t equal to 0. Now, at a non-zero temperature, mu is in general not equal to EF, at t not equal to 0. But you would see that for the electron gas, because EF is a very large number, as I said before. So, therefore, for all practical purposes, you can take your mu to be the Fermi energy, because the correction term that comes because of the temperature dependence is very, very small, right. So, in our case, this situation will not arise. So, we will fix the Fermi distribution with mu replaced by EF. That will be the case for us even at non-zero temperatures, because EF for the electron gas in a metal is a very, very large number, right. So, at a non-zero temperature, if you plot this curve, then it would look like this only, because of what I explained over here. All the states up to up to the point you reach here are nearly occupied, right. So, they are all occupied. So, therefore, F for them should be 1, which means the probability of the occupancy is 1, they are surely occupied, and then there will be a drop, and then it goes like this. So, the states that were previously unoccupied are now occupied with some finite probability. The probability of their occupancy is not 1, and the probability of their occupancy has also dropped from 1, right. So, these states are now, these states have been replaced by these states, right. And if you see, you can easily see that this point will be nearly 1/2. F will be 1/2 if you put E equal to EF at finite temperature. You can check that, right. So, now coming to the expression for specific heat. So, now that you have done phonons, you know how to calculate specific heat. So, the only degrees of freedom that we have here are the electrons, right. So, what you do is you say what is the energy of electrons at any temperature T, okay, that will be equal to their ground state energy u0 plus the energy that they have gained. So, let me call this as u tilde. So, this is the total energy which is equal to the ground state energy plus the energy due to these excitations. All right, this is the energy due to the excitations above the Fermi energy at any temperature T. So, if you take the temperature derivative of this, you will get the heat capacity. But if you take, for instance, volume, so for instance, if you take u tilde volume equal to then u naught volume plus u volume, right, then it will be your volume specific heat per unit volume, isn't it so? Then it will be specific heat per unit volume. So, therefore, CV is for constant volume, but here it is not molar, it is the specific heat per unit volume and this will be simply the derivative of this delta u tilde V by del T. The derivative of this term would be 0, this is the 0 temperature energy, and you are left with just del u V del T. So, if you can find u V, your job is done, and u naught, which we spent more than 45 minutes of the lecture on, has no role to play in the specific heat, because that is the ground state property, right, that has nothing to do with excitations. So, how should we get u V? So, calculation, the exact calculation of u V is quite cumbersome. You won't like it, you won't gain much if I do it here. So, we will do a sort of a rough estimate of this u V. So, how should we estimate u V? So, the way to estimate u V is that what is the density of states at the Fermi energy, that is DEF. Okay. So, what you do is you say that number of states per unit volume within KBT of EF will be how much? Who will answer this question? How many states are there within KBT of EF? So, I am talking about can you count the number of states that are there within this shaded region? So, this is your KBT, by the way, this width. This is KBT from here to here. Okay. So, this width is of the order of KBT. So, this will be how much? So, if you assume that the density of states doesn't change much within that region and it is equal to the density of states at the Fermi energy itself, then it will be simply the density of states at the Fermi energy times KBT, the width of that region, right, because that is the definition of density of states. So, that is the number of states. So, therefore, the number of electrons that you are exciting from here to here will be how much? Will be some fraction of this, the fraction being decided by the probability factor, right. So, therefore, you can then write that your number of excited electrons per unit volume comes automatically because this density of states is itself defined as per unit volume, right, per unit volume. This will be some factor, let us call it alpha times DEF times KBT. So, you got the number of electrons. Now, you can assume very roughly that the average energy of each of these electrons is KBT, because you are at temperature T, you assume that the energy of each of these electrons is kBt. So, therefore, what is the total energy of your system? The energy of your system will be this quantity multiplied with kBt, right, because these many electrons you have excited, and these each of these electrons is carrying on an average an energy kBt, right. So, the energy of your electron gas at any temperature T, which is this quantity U, UV, yeah, UV at any temperature T, will be of the order of alpha DEF times kBt square. You understood why this square term comes here? Because each electron on an average has an energy kBt, and the number of electrons are these many. So, just multiplied, you got the total energy, right, average energy. So, the energy will be of the order of this. The quantity alpha we haven't fixed, but alpha will be some number between 1/2 and 0. So, now you take the derivative and you get the energy, and you can use this expression to write dEf in terms of 3n by 2EF. So, then you will when you will do this, you will see that first thing you see is that the moment you take temperature derivative, you get a linear temperature dependence. So, the linear temperature dependence is already settled. So, the temperature dependence and the prefactors also you can work out. So, you can do it nicely yourself, and you should be able to write it as 3 alpha kBt by EF multiplied with 3/2 n kB. So, I have purposely written it in this form, because for a free electron for a classical gas it will be 3/2 n kB times T, and here it is a factor of EF sitting at the denominator, right. So, suppose you are at a temperature T equal to 100 Kelvin, okay. Your EF is of the order of 10 to the power 4 Kelvin, right. So, therefore, your measured CV is 1/100th of this factor 3/2 n kB, which is the classical value, and which is what we wanted to prove. So, therefore, at 100 K, for instance, the CV is approximately 1/100th of 3/2 n kB, which is the classical specific heat near room temperature, and therefore, we have shown that the actual specific heat will be 1/100th of the classical value, and it will vary with temperature linearly. Okay. So, we will stop here.